Hello, everyone. I am Mitsunori Waimura of Ritsumeikan University. Let's start the 6th week of the Advanced Topics in Robot Control. This week, I would like to newly introduce iterative learning control and repetitive control. Iterative learning control and repetitive control generate desired motions by learning the feed-forward torque from repeated control trials. These methods are similar to practice swings in sports. In a variety of sports, such as those shown in these figures, practice swings are considered very important and have been incorporated into the practice of professional athletes. If you have worked hard on sports, you are keenly aware of the importance of practice swings. When you do practice swings, you repeat the same motion over and over again, and you are able to create the motion more precisely as you want. Therefore, the practice swings seem to make the trainee learn the muscle strength required for the desired motion through the practices, and create the desired motion precisely. Iterative learning control or repetitive control is a method of achieving CP control by learning the torque required to generate the desired motion from control trials. Now, to understand the principles of iterative learning control and repetitive control, let's consider the simplest one-joint robot that moves in a plane where gravity can be ignored as shown in the figure. Let us apply iterative learning and repetitive control to this robot to understand the structure and stability analysis of the basic control method. The motion equation of such a robot can be expressed as this equation. As with the computed torque method and adaptive control, the control objective of iterative learning control and repetitive control is CP control. Therefore, the control objective can be expressed mathematically in this way. In iterative learning control and repetitive control, the feed-forward input tau FF is learned through control trials. The feed-forward input tau FF1 on the first control trial is initialized using an arbitrary time function. If you don't have a special purpose, tau FF1 during the first control trial is initialized with 0. The controller is designed by adding the feedback inputs to this feed-forward input, as in this equation. These feedback inputs have the same effect as in the computed torque method and adaptive control, which allow the actual joint angle and angular velocity follow the desired ones. As with the computed torque method and adaptive control, iterative learning and repetitive control can achieve the control objective if the feed-forward input tau FF becomes the torque tau D required to generate the desired motion. In iterative learning and iterative control, the tau FF converges to tau D by learning from control results obtained from control trials. After the first control trial is completed using the controller, we should return the joint angle and angular velocity to those at the initial time of the first control trial in iterative learning control. The second control trial is performed with the return joint angle and angular velocity at the second initial time. This is similar to practice swings in sports. In sports practice swings, the pose of the person who starts the swing should be the same each time. Iterative learning control aims at making the subsequent trajectory follow the desired trajectory by making the initial state the same each time. In repetitive control, the second control trial starts immediately after the first control trial. Therefore, the joint angle and velocity at the initial time of the second control trial will be those at the end of the first control trial. In other words, repetitive control is used for motions, such as walking or running, where the next control trial must be performed immediately after the control trial. Therefore, the desired motion must be a periodic motion in which the state at the initial time and the state at the last time are the same. Repetitive control has the advantage that, unlike the iterative learning control, it does not require the effort to return the joint angle and velocity to the same state each time. Although the iterative learning control and the repetitive control differ in the handling of the state at the initial time of each control trial, we can use the same controller for both iterative learning and repetitive control. In iterative learning and repetitive control, we update the feed-forward torque tau FF2 in the second control trial by adding the control error in the previous control trial to the previous feed-forward torque tau FF1 in this way. Intuitively, this iterative learning law can be interpreted as adding the missing torque from the previous control trial to the next control trial to reduce the control error in the next control trial. For the third and every KDH trial, we update the feed-forward torque tau FFK by adding the control error in the previous control trial to the previous feed-forward torque tau FFK1. Iterative learning control and repetitive control repeat this learning process to learn the feed-forward torque to achieve the control objective. Now let's create a MATLAB simulation in order to master iterative learning and repetitive control. To make the simulation easier to create, let's reuse the simulation of the computed torque method for the single joint robot. Since we can more easily implement repetitive control than iterative learning control in a simulation, Let's implement the repetitive control. Therefore, let's use a trigonometric function to set a periodic trajectory for the desired joint angle. Let's set the period of the desired trajectory 1 second. Then, the desired angle is, for example, QD equals sin 2 pi t. Let's set the desired velocity based on the desired angle. To input the learned feed-forward torque to the controller block, let's add a tau ff to the input of the controller block. Let's add the error feedback to this tau ff to give the actuator torque tau. This part is same as the computed torque method. To use the feed-forward torque tau ff plus the control error as the feed-forward torque in the next trial, let's calculate that value tau ff next and output it from the controller block. We want to use the feed-forward torque tau ff next calculated now as the feed-forward torque for the next cycle after 1 second, so let's use a delay block to delay the signal. The delay block is located in the continuation of the Simulink library browser. Let's set the delay time of the delay block to 1 second. Let's input the feed-forward torque tau ff next into the delay block, and let's input the output of the delay block into the controller block as tau ff. This completes repetitive control. To check whether a trajectory tracking control has been achieved, let's display the desired joint angle and the actual joint angle on a single graph. Let's also display the feed-forward torque tau ff in a graph to see how the repetitive controller learns the feed-forward torque. Now, let's take a moment to create a simulation. Next, we will prove the stability of the control system when we use iterative learning and repetitive control. As we experienced in the simulation, learning control is very simple. However, stability analysis is very complicated. Generally, we need such a complicated analysis show the validity of a simple control method. Let's first subtract the torque required to generate the desired motion tau d from both sides of the learning law. Then we have terms on both sides for the errors between the feed-forward torques tau ff and tau d. We will confirm whether this error is reduced on each control trial. To derive the magnitude of the feed-forward torque error, let's square both sides. Also, let's put together the term for the control error on the right side as Z1. Then we get this equation. In addition, let's integrate both sides in time for one cycle to derive the error for one cycle, where the large D is the time of one cycle. To simplify the equation, we define the integral of the square as the norm. Since the content of the norm on the right side consists of two terms, the feed-forward torque error tau ff1 minus tau d and the control error term z1, we can expand the right side to obtain this equation. Then, the left side is the magnitude of the feed-forward torque error at the second control trial, and the first term on the right side is the magnitude of the feed-forward torque error at the first control trial. Therefore, if the second and third terms on the right side are smaller than 0, it can be shown that the feed-forward torque error becomes smaller by learning. In the following analysis, we mainly analyze the second term of the right-hand side. To do this, let's subtract tau d from both sides of the robot dynamics with the learning control applied. Then the term for the feed-forward torque error on the first control trial appears in the first term on the right side. Subtracting I bar times qd dot minus q dot divided by the alpha from both sides, and summing the left side with z dot, we get this equation. To derive the product of the first feed-forward torque error and z1, we multiply both sides by z1. Integrating this equation by one cycle in time, we can calculate the second term on the right-hand side of the last equation of the previous slide. If we integrate the left side, we get a term about the square of z1, so we'll call it v1 like this. If we use this to calculate the time integration, we get this equation. This right-hand side first term is in the same form as the right-hand side second term in the last equation of the previous slide. The content in the curly bracket of the right-hand side second term has almost the same structure as Z1. Then, by defining a positive constant C such that the magnitude of the content of the curly bracket does not exceed the magnitude of Z1 multiplied by C, the right-hand side can be represented like this. Substituting this equation into the second term in the equation of the previous slide, we get this inequality. This inequality roughly represents that the second feed-forward torque error will be less than the first feed-forward torque error. However, we need to consider the function v1. So, let's remember the initial state settings in iterative learning and repetitive control. In the iterative learning control, v1 is 0 at the beginning of each control trial, because we return the joint angle and angular velocity to the same initial ones. In the repetitive control, since the initial joint angle and angular velocity at the second control trial is those at the end of the first control trial and the desired trajectory is the periodic trajectory, v2 at the start of the second control trial is the same as v1 at the end of the first control trial. Using these to define a function ni which combines the feed-forward torque error and the function v for the ith control trial, we can prove that n2 is smaller than n1. In other words, the sum of the feed-forward torque error and the control error is shown to decrease as the learning process is repeated. This property holds for all control trials if we use the same learning law for all control trials. Therefore, it is shown that the feed-forward torque error and control error decrease with the progress of learning, and the control error converges to 0 after a sufficient number of control trials. These results prove that CP control can be achieved by the iterative learning control and the repetitive control. As shown above, the stability analysis of the iterative learning control and the repetitive control is very complicated. However, since the iterative learning control and the repetitive control are very simple, they have a great advantage in that they do not require detailed information about the robot or a lot of numerical calculations. Iterative learning and repetitive control can also be applied to multi-joint robots with nonlinear dynamics defined by this equation. This was proposed by Arimoto and Kawamura et al. In 1984. This paper has been cited in over 3,000 papers and is one of the leading papers in the field of robot control. First, In the first control trial, the feed-forward torque vector tau ff1 is initialized using arbitrary time functions. Typically, we adopt a zero vector as the initial feed-forward torque. The actuator torque vector tau is designed in this way using the feed-forward torque vector and the error feedback terms. This is the same as the iterative learning and repetitive controller in the case of the single-joint robot applied to each joint of the multi-joint robot. The learning of the feed-forward torque is also done by applying the same learning law used for the single-joint robot to each joint. Therefore, iterative learning control and repetitive control are extremely simple, even when used for a multi-joint robot. The computational cost of these equations is significantly less than that of the computed torque method or adaptive control. Therefore, iterative learning and repetitive control has the advantage that it is very easy to implement for robots with many degrees of freedom and consumes few computational resources. Now let's create a simulation that implements repetitive control on a multi-joint robot to master the iterative learning and repetitive control. To create the simulation easily, let's reuse the simulation in which the computed torque method is applied to a multi-joint robot. You can create the rest of the simulation in the same way as for the single-joint robot with the repetitive control. So let's take some time and create a simulation. We can prove stability by essentially the same procedure as in the case of the single-joint robot. However, the calculations during the analysis are extremely complex compared to the case of the single-joint robot due to the nonlinearity of the robot dynamics. Therefore, we will not cover it in this class. If you encounter a situation where you use iterative learning or repetitive control, let's learn to handle the nonlinearities after understanding the stability analysis for the single-joint robot case in detail. That concludes our introduction to iterative learning and repetitive control. Finally, I would like to introduce two advanced repetitive control. The first is the application of repetitive control to periodic motion, including collisions. In the control methods we have introduced so far, the structure of the robot dynamics is assumed not to change during the control. However, when we actually use the robots that perform various tasks, the structure of the dynamics changes when the robot touches something. This study deals in particular with collisions. Collisions occur periodically, for example, when the robot is hammering down nails with a hammer or when it is walking. In such cases, we need a control method that can guarantee the stability even if the collisions occur. In this study, the authors proposed a control method to generate the desired periodic motion that includes the collisions. As shown in this movie, the trajectory of the robot hand converges to the desired trajectory. The second advanced repetitive control method is an energy-saving control method that uses resonance. This control method was introduced in a previous class on passivity-based control. This control method adaptively optimizes the stiffness of the variable elastic elements attached to each joint of the robot in real time to reduce energy consumption and generate periodic motion. The authors extended this control method by applying repetitive control. Specifically, the repetitive control is applied to learning motions with low energy consumption. This experiment confirms that the energy efficiency is about 3 times better than when the motion is not learned. The simultaneous optimization of stiffness and motion can produce the same motion with about 1/16 the energy consumption compared to not using either. Finally, I would like to introduce homework for this week. This week's homework is to create the MATLAB simulation I described this week and submit it as a report. In the report, Please include the figure of the simulation model of Simulink, the program source of the robot dynamics block, the program source of the controller block, the simulation result graph, and the explanation of the simulation contents and the simulation result. Please submit the created report through Manabar. That concludes this week's class. Thank you for your hard work.